Welcome back, Night Owls. This is Dr. Nighttime. And tonight, we're going over a variant of the Monty Hall problem. And this particular variant actually fooled the professor of one of my students. Now, yes, the original Monty Hall problem itself is infamous for fooling many well-established mathematicians. But what happened here was that my student was given this variant as a homework assignment, and we discussed it and talked it over, and then he submitted the answer that we had talked about and did not get full marks. And the instructor's answer and the instructor's explanation seems to have a particular flaw that I'll get into. But first, for those of you who aren't already familiar, what's the basic Monty Hall problem setup? So, it describes a game show where the contestant is shown 3 closed doors. One of the 3 has a prize behind it. Contestant gets to choose a door. Now the host knows where the prize is. And to make things interesting, if you think about it, the contestant has chosen one of the 3 doors. Now that means that of the 2 remaining doors, at least one of them doesn't have the prize. So, the host, by opening that door, will not reveal whether or not the contestant already chose the correct door, right? That's irrelevant, and won't be revealing where the prize is. So, the host can open a door that doesn't reveal where the prize is. Now, the contestant may choose to switch doors. And the question is it beneficial to switch doors, or beneficial to stick with the original door, or does it not matter either way? And it can be easily shown that it's strategic to switch doors. The simplest explanation is that you had a contestant had a 1/3 chance of guessing the correct door to begin with, and that 1/3 of the time, switching will actually lose the contestant the game, and that by standing, sticking to the original door, by standing, the contestant will win the game 1/3 of the time. Now, since there are only 2 doors to choose from once the host has revealed that empty door, that means that there's a 2/3 probability that you win if you switch. So probability of winning without switching would be 1/3, probability of winning with switching would be 2/3. Okay, now what's this variant? Now the host uses a different procedure to reveal the door. Most of the time the host will just reveal one of the doors, but beforehand, using a randomization device, the host will sometimes just immediately end the game. Imagine spinning a spinner that some fraction of the time says, end the game now. In that case, if you trigger the end game scenario, the host will reveal the contestant's door, and if the prize is behind the door, then the contestant wins, and if not, the contestant loses. And that's the entire game. And let's let Q be the probability that the randomization device will dictate to trigger the end game. And the question is, does this value of Q have an effect on the winning strategy? And at first glance you think, well, probably not, right? Because if the end game is triggered, then there is no strategy, right? You don't have any choices to make. And if end game is not triggered, you're back in the same original scenario you were in the original problem. And that logic would be completely correct. But let's take a look at the algebra just to show it a little more thoroughly. So here we have the tree diagram, or at least most of the tree diagram, for the conditions of the game, right? And for how the game could progress. It's already enough of an eyesore. I've only included all the probabilities for the cases where the prize was behind door number 1. Clearly, by symmetry, it doesn't matter whether the prize was behind door number 1, door number 2, or door number 3. So, supposing, without loss of generality, that the prize is behind door number 1, contestant could choose that door, or either of the other 2 doors, each with probability 1/3. Now, if the contestant chose the correct door, then with probability Q, that door will be revealed, right? Endgame will be triggered. With probability 1 minus q, endgame will not be triggered, and the remaining 2 doors will be revealed, each with probability 1 minus q over 2, right? In that 1 minus q chance of no endgame being immediately triggered, then you split the possibilities, right? Half of the time in that situation you go open door number 2, half the time you open door number 3. Now clearly, if the contestant had chosen the correct door right away, if that door is revealed, there is no chance to switch, right? It doesn't count towards anything. Whereas, in the other 2 cases, you don't win if you switch, but you do win if you stand. And those will have probability 1 minus q over 18, right? 1/3 times 1/3 times 1 minus q over 2. But now let's look at what happens if each of doors 2 or 3 are chosen. Then, with probability q, that same door that the contestant chose will be open. Right? And contestant instantly loses, but the question about whether or not to switch, that's irrelevant. So you get these NAs here. Meanwhile, with probability 1 minus q, that remaining door would be open. So if the prize is behind door number 1, the contestant chose door number 2, then the door revealed would be door 3 with probability 1 minus q. And the opposite if the contestant chose door number 3. Right? With probability 1 minus q, door number 2 would be revealed. Each of those cases has probability 1 minus q over 9, right? 1/3 chance for the prize being behind door number 1, 1/3 chance for the contestant choosing that specific door, and 1 minus q chance of the end game not being triggered and the game proceeding as normal. Combines for 1 minus q over 9. You combine all these probabilities, and you get that probability of winning if you switch is 2/9 1 minus q. Probability of winning if you stand is 1/9 1 minus q, right? 1 minus q over 18 plus another 1 minus q over 18 is 1 minus q over 9. Now, let's multiply all those by 3 for the 3 different doors that the prize could be behind. And we get that you'll win if you switch with probability 2/3 1 minus q. You'll win if you stand with probability 1/3 1 minus q. And with probability q, the game will end with no choice. Endgame will be triggered. No surprise about that. So we see switching is clearly still strategic. You have a greater chance of winning if you switch than winning if you stand. So how did this instructor get it wrong? The instructor tried to argue probability of winning and switching, or winning by switching, was going to be 2/3 times 1 minus q. And the instructor tried to argue that if that expression is greater than 0.5, then switching is a winning strategy. Otherwise, it's a losing strategy. Which, alright, you could sort of see the argument that, yeah, winning strategy means winning more than half the time. That's an imperfect argument. I'll look at more of the details in the flaw. I'll look at the flaws in more detail and point out the flaws in more detail momentarily. But what the instructor was trying to argue was that if q is less than 1/4, this expression is more than a half. That's correct. And if q is more than 1/4, this expression is less than a half. That's correct. And then tried to argue that because this expression is less than a half, that means it was preferable not to switch. And here's why that's wrong. First of all, the total probability of winning could still be greater than 1/2, because you also need to account for probability of winning due to the game just immediately ending. But also, we're not really interested in your overall win rate. We're interested in, you could either view it as the conditional win rate, conditioned on having the opportunity to switch and either taking that opportunity or leaving it, or interested in the comparison between probability of winning when you do switch versus winning when you don't switch. Either of those two perspectives would say, all right, either we need this conditional probability to be more than 50%, or just that probability of winning when you do switch is greater than probability of winning when you don't switch. And so if you want to look at the overall probabilities, the win probability is 1/3 Q. That's for probability Q that endgame will be triggered. 1/3 of the time, that means you just instantly win. Plus 1 minus Q that the game continues, in which case there's a 2/3 chance of winning if you switch. Compare that to 1/3 Q of winning by immediate endgame, plus 1/3 1 minus Q if you decide to stand. Comparing these two numbers, switching is always better. Now, it is true that if Q is more than 0.5, you do the algebra on this. If Q is more than 0.5, you do have less than a 50% chance of winning. So how can we say that we have an optimal strategy if we still lose more than half the time? Well, in those games, consider the case where Q is 0.99. That means almost every time there is no real strategy and it's just going based on the door that you chose. Then you would just consider this a difficult game. You're not likely to win more than half the time. But that doesn't mean you're using a bad strategy. It could mean that in such a difficult game, even the best strategies lose more often than they win. And that would be the situation if Q were more than 50%. So the conditional probability of winning if you switch is still 2 out of 3, right? Conditional on having the opportunity to switch and taking that option to switch. Right? Conditional probability is still 2 out of 3. I hope you found this useful. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. Until next time, this is Dr. Nighttime wishing you a good night.